Hello everyone and welcome to Lattix training. My name is Neil Langmead. I'm a member of the Lattix technical support team, which is based in Boston, United Kingdom and Germany. Today we're going to give you an introduction to Lattix and this training. We're going to show you the motivation for software architecture and analysis and learn about some of the things you can do with Lattix. Firstly, by way of introduction, our company is called Code Clinic and our motto is building technical wealth. We want to eliminate technical debt, and instead of building software which contains that technical debt, we want to get it right first time and help software engineers to build high-valued technical digital assets correctly first time. We were founded in 2018 in Boston, and we acquired the Lattix software in 2021. We provide training, consulting, and implementation. We provide systems, software architecture analysis, and refactoring services. We can help you with software build and test strategies, including AI, and we also have deep expertise in functional safety and compliance. For example, with the automotive standards ISO 26262, ASPICE, the medical FDA 62304, and the general industry standard 61508. We also provide consulting for CI DevOps projects to help you to accelerate your software quality, software security initiatives, and provide essential automation. So that's the company. What about the product? Lattix is the product, founded over 20 years ago now in 2004, developed a unique tool suite applying dependency structure matrices, or DSMs, and their methodology to complex software systems. We're now a leading global supplier and provider of software and system architecture analysis solutions with more than 1,200 customers spread across the globe in 30 different countries. Our product supports many different languages and integrations with tools and DevOps environments and systems. Here are some of the use cases as to why you might consider using Lattix. Perhaps you have a difficulty with your build system. Software is getting more and more complicated these days, and the way we build software, usually because of that increasing complexity, is taking longer and longer to build software effectively. Maybe you want to improve your build. If you can improve your build, generally you see improvements in the release cycle as well, because almost every stage of the DevOps pipeline uses the software build at some point. For example, static analysis or unit testing. If we can improve the build and optimize the build, that will save many developer hours and reduce the cycle time it takes to release a new version of our software. We postulate this sometimes as the null release problem. The null release is how long does it take to rebuild and recertify your software with a one line of code change. So I change one line of code. What do I need to do to re-release the software with that line of code change? That's where we're thinking about. It's a deep question. Often there are automation opportunities with the null release, in that we are maybe doing things manually that we could automate. That is part of the analysis of the software build to see if we can find some improvements. Maybe you want to move from a monolithic structure or architecture to more of a microservices, and you want to increase modularity for that precise reason, to accelerate the build of the software, or to make life easier in the maintenance phase. This is something that you can do with Lattix, helping you side by side. Or you want to componentize. Maybe you have a large C++ system, for example, or Java system, and you want to divide that up into small reusable components. For example, with JFrog's Artifactory or Conan, and you want to deploy smaller components and help maintenance in that way. That's something you can use Lattix for too. What about architecture discovery? Do we even know what our current architecture looks like? And this is a key use case of Lattix, just simply discovering how our architecture looks at the moment. We can do, for example, a visualization of all the dependencies in the system. That's what the DSM, or dependency structure matrix, is perfect for. We can look at the coupling in the system. Maybe one component is using a different component that it shouldn't use, or this component is using this one as well. So there's a bidirectional coupling, which is generally undesired. We can help you identify where those couplings are occurring in the system and give you hints to remove those dependencies and to decouple your system. Decoupling is good. We generally want to decouple, and so often when you visualize the architecture, discovering the architecture and the structure of your applications and libraries, there are opportunities that present themselves to decouple and again improve the structure. Refactoring, we've just touched on that. This is a key use case of Lattix and our customers. Maybe you want to take the opportunity to reuse certain parts of the system, but they are depending on other parts of the system we don't want to reuse. Generally, we want to decouple those first, and then that gives us an opportunity to refactor and to promote, for example, code reuse or test reuse. Any kind of reuse of our digital assets is to be welcomed, because if we can reuse our software, we get extra value from that software usage. So we might want to refactor cycles or couples, or simply spaghetti code that is just a ball of spaghetti that's evolved and has undergone some architectural erosion. Another major use case is the functional safety world, or FUSA or FUSI, where, for example, we have use cases like freedom from interference, where we have a higher rated ASIL part of our system and a lower rated ASIL different part of our system, and we need to prove that the safety system of the lower ASIL cannot interfere with the higher rated ASIL. And so that is freedom from interference. We can help build the case for freedom from interference and prove that to the certification authorities, for example. Traceability. It's not just source code that we can visualize in Lattix, it's complete system and other domain dependency informations, such as requirements, model information, safety domains as well, like HARA and FMEA. You can actually import data into Lattix and visualize the relationships between different domains. And in doing so, you uncover opportunities for traceability improvements or traceability gaps. Functional safety also requires metrics such as cohesion, coupling, and stability. These are provided out of the box by Lattix, and we'll see the use case for that in a separate training for functional safety. We've touched on DevOps a little bit and building the software, but building is just part of the software delivery process. We also have tests, we have deployments, we have perhaps different configurations of the software that we build and we ship. So how do we manage this? You can see here in this simple Jenkins pipeline that the test phase has been parallelized. Many steps that were only sequentially possible before are now implemented in parallel. And this is because we've identified opportunities from the dependency structure matrix for independently running some tasks or the build of some components that are linearly independent of each other. So if we can get that desired coupling, decoupling, that improves our DevOps outcomes as well. And similarly, our test outcomes improve with what we call a smart test approach. As the number of unit tests typically increase, as the code complexity increases, we are often working with systems with over 1 million unit tests. You cannot feasibly rerun all of those unit tests every time something changes. So you have to have a smarter approach. We calculate the impact of a change and to the transitive closure of that change, meaning that we calculate the complete effect of a change to our system, and we then only have to rerun the tests that are directly or indirectly affected by that changed component. We can also import coverage data into the dependency structure matrix in a heat map form so that you can see areas where you have high coverage, where you've met your coverage threshold, that would be green. Other areas where you're approaching a warning level, that would be orange. And in the heat map, other areas where you maybe have not reached your coverage threshold, that would be shown in red in the Lattix heat map. So these are some of the use cases. Maybe some of these apply to you. Maybe you're focused on one of these. Whichever, we will guide you through each of these use cases through the training. A little bit more of a deeper dive into the functional safety solutions. We have seen, for example, the automotive standards, ISO 26262 here from table 3. Almost all of the functional safety standards derive from the 61508 standard, and hence they have very similar language and similar requirements for software architecture, testing, static analysis, control and data flow analysis. And you see a typical example here in table 3, where in our principle for software architecture design, we're required to show a hierarchical structure of software components. That's clause 1a, and that is perfectly demonstrated, of course, by the dependency structure matrix. Also 1d, high cohesion. We have a cohesion or connectedness metric that we track. And restricted coupling, 1e, we can show the amount of coupling as a percentage, as a metric in Lattix as well. We can also integrate with static analysis solutions and dynamic testing tools. Also, worst case execution time data can be imported into the dependency structure matrix so that you view all of that data through the prism of the software architecture. Lattix has been applied to many functional safety projects, including in the automotive and medical domain. Here you see a screenshot of an ASPICE process where you have different SWE, software engineering levels, 1, 2, and 3, and software validation exercises at 4, 5, and 6 corresponding to those steps. We have a full traceability solution for ASPICE that is in use by many customers today. So if you want to know more details about our functional safety, we will do a separate training on and deeper dive into these topics. So today we're going to look at learning to use Lattix. It's a 4-hour training. It's an introduction, and you can find the documentation for this training at the website. I'm just going to jump to this website now. It's learning to use Lattix. Over these 4 hours, we take you through the first 6 modules, and the introduction is what is architecture. I'm going to show you a little bit about what is architecture, how we see architecture, and the motivation for using Lattix, and then the process, the steps to apply Lattix to your system. That's what we're covering today. And in future sessions, we will look at working with dependency structure matrices, working with a conceptual architecture diagram, enforcing and maintaining architecture through rules. We'll look at the different types of rules that are possible in Lattix, how to reorganize a system within Lattix that you maybe want to improve or to refactor, hence removing dependencies as we've discussed. And then part 6, using the repository, using the trending analysis to see if we're going in the right direction for our projects. So looking at the introduction, what is architecture? Going back to the slide, you've maybe seen a diagram like this, usually consisting of boxes and arrows that show incoming and outgoing relationships between different components. It's a good way of seeing the dependencies between subsystems and between parts of our systems. However, you can quickly see that it's hard to determine which dependencies are bad. And you can imagine in huge systems, this diagram quickly becomes cluttered, and indeed it becomes completely unusable in many cases, just consisting of a thick body of black lines, and it's very difficult to see what is happening. The dependency structure matrix, in contrast to boxes and arrows, provides you that accurate big picture. So we see the complete system overview, but we can also drill down and get the required accuracy for a particular component that we're interested in. And very often, this is the first time we've seen at a high level the structure of our system in this dependency structure matrix, or DSM. It's the most scalable way to visualize dependencies and identify problems of architecture and, for example, between our layers. How do we read a dependency structure matrix? We'll go into this in a lot more detail, but essentially we look down a column to see what a component is using, and we read across the row to see what a component is used by. So for example, server here in the middle of our system is using the include relationships 3,392 times. Modules here is using server 1,938 times, and OS Win32 is using modules 4 times. So we get an idea of how strongly dependent one system is on another, or how strongly coupled one system is to another, and that's the using relationship. So the columns are using, the rows in contrast are used by. So for example, we would read across the row and we would say it like this, that server is used by support once, and include is used by support 3 times, and include is used by test 2 times. What do we mean by using in this context? Well, it's any relationship in this particular language, and this is a C++ example. That could be an include, a define, a global variable usage, could be a type. Pretty much anything from the abstract syntax tree of C and C++ is visualized and counted as a dependency kind in Lattix. So that's essentially how we read a DSM. Immediately looking at this picture, and we'll get lots of practice reading DSMs, we can see that Lattix has organized the system, and these black boxes here are what we call partitions, and we will teach you how to partition your system. That is an organizing by usage of your application. So by default, you load Lattix. We provide the alphabetical listing of components. However, that doesn't always reflect the best way the software is being used or structured. So we do something called partitioning, and that groups software by usage. It puts things that are heavily used at the bottom, like the include here. You can see the include directory is used by pretty much everything. And it will put things that are using other components but not used themselves at the top. For example, test is at the top of the system because test is using things and nothing is using test in this case. You also see relationships. So after partitioning, you see relationships above the diagonal sometimes, and that means lower level components are using higher level components, which may be undesired. Looking at this example, we see that modules is using server, and server is using module, and that may not be desired. You can see that the correct relationship is probably modules to server. That has the strongest dependency. And the incorrect one or undesirable one is from server to module. And so you can see that we set a rule here to say that server should not use modules. And this is a violation. That's why you see the red flag in the corner here. And so this is a rule violation. And so immediately we see the information that's conveyed in the dependency structure matrix. We see lower layers calling higher layers. That might be something that we want to fix later. Generally, we want to see most relationships below the diagonal after partitioning of a dependency structure matrix. Then we have the opportunity to track key metrics such as code coverage or complexity or stability or any of those metrics, so that we see in a traffic light system where we are compliant with our standard, where we've achieved our threshold, and where there's some work to be done. And that is all done through the prism of the software and system architecture. And so this is Lattix. You can also see trending diagrams in the background there that we're tracking improvements. We want to see complexity generally be stable or going down ideally. We don't want to see increasing coupling. And so we're just kind of keeping track of the health of our software architecture as we go. Here's an example that we use throughout the training. It's called ISO AGlib, and it's an open source piece of software which has an architecture diagram, and that's what you see here. And very often we get a lot of information from architecture diagrams. Maybe you have one for your system. In this particular system, we have 4 layers, 5 including scheduler, and communication is at the top. We have data link and network management, which are colored modules. These are mandatory parts of our system. And we have these gray optional modules here as well, which may or may not be delivered in certain configurations. And you can see the desired direction of usage. The hardware drivers shall only be used by the abstraction layer, shall not be used directly by communication, for example. So you don't want to see communication use hardware and drivers. That's similar to if you're working with AutoZAR, for example, on the RTE. You don't want the applications directly using the RTE. They go through the basic software packages and use the APIs in a conformant way. This is very often established at the beginning of a project, and it doesn't change, right? But the software changes. So we get divergences from the expected intended architecture from the real implemented architecture. And so we can show those differences. We also can enforce layering rules, and modularity within the system is important, obviously. For example, we don't want task controller and process data to be using each other because they should be independent subsystems. And so we can specify certain components are mandatory and certain gray modules are optional. And we can ask Lattix to preserve that independence and enforce that as a rule, that these components shall permanently be independent from one another. And I'll just quickly go to show you that in Lattix. This is how that system looks like. And the COM component that we've just looked at there, you can see relationships between these subsystems here, which should be independent according to our architecture diagram. And we have the opportunity to create independent subsystem rules here to enforce that modularity. And you can see those violations in the code, violating that intended architecture that we've just looked at. So that's the first point. What is architecture? That's the motivation. Next, why use Lattix? Lattix provides powerful ways, as we've just even seen with this short introduction, to visualize, analyze, communicate, and enforce the architecture. We've got comprehensive support for languages, databases, and frameworks. It's unique that you can combine multiple domains in a single project as well. So for example, in this ISO AGlib system that we've just looked at, I don't just have the code, I've also connected requirements and safety information and people information from the Git repository in, so that we will explore that later in the training to see multi-domain information. And this is a huge powerful part of our solution. And the DSM representation is the most scalable representation of large systems. Some of the reasons for using Lattix we've touched on: architectural discovery, re-engineering, enforcement of architecture. Impact analysis is a very important use case, finding the cost of a change or the result of an impact of a security vulnerability, for example, and then tracking, measuring, and reporting our architecture build to build, for example, in the DevOps context or in a Git workflow is super important. So that's the first part. And then the Lattix process, steps to apply Lattix to your system, how to produce the DSM in the first place. We'll take you through step by step. How to create initial DSM for your system and load the data into Lattix. And then step 3, to reorganize your project to reflect the intended architecture. Step 4 is then to set rules, as we've just seen with ISO AGlib, for system interdependencies and external libraries. So do look at this first part of the training, succeeding with Lattix Architect and Lattix Web. Go through these slides. What is architecture? Why is Lattix? And the Lattix process. And we will take you step by step through this journey, and you will build your first dependency structure matrix using this ISO AGlib example, creating the DSM and visualizing the architecture for the first time. That concludes this introduction. Thank you for listening. And our next topic will be working with dependency structure matrices. Thank you.